Welcome to the channel. So in this video we will talk about the nucleophilic attack by hydride on aldehydes and ketones. So we will start from a compound which is sodium hydride, NaH. This sodium hydride is ionic in nature. Ionic in nature. It means it can actually split into Na plus and H minus. Being more ionic, this H plus, H minus hydride ion basically do not act as nucleophile but act as a good base. This hydride can only act as base, and it is really a good base but not a nucleophile. This is because acid base reactions are fast and H minus is NaH is a more ionic and it will produce H minus in a very fast rate. So whenever the H minus form, it actually takes the acidic hydrogen. Means we cannot suppose that this reaction would happen. And let's suppose we have this carbon group, and on adding NaH and sodium hydride, this H minus would attack on this carbon group and we'll see a formation of alkoxide ion. This won't going to happen. This will not going to happen because this is more ionic in nature. It just take acidic hydrogen. Let's suppose if we have something like HX. X can be any atom. Most of the any atom you can take. So on adding NaH, you will see H minus will take this acidic hydrogen and hydrogen gas releases. So this is basically acid base reaction. But if we just suppose that we can make this carbonyl compound to alkoxide like this reaction would be very beneficial for us because after forming this alkoxide we can protonate it easily and we will have alcohol. We can reduce it, right? So we just want something here which can act as a nucleophile. We just want hydride as nucleophile. Hydride as nucleophile. But how we can achieve it? So we have a really good reagent which is sodium borohydride. NaBH4. The main thing is that this sodium borohydride is basically soluble in water and alcohol. Soluble in water and alcohol. So in NaBH4 you can see we have tetrahedral BH4 negative anion, and here this boron and hydrogen bond is relatively more covalent. This bond is more covalent as compared to NaH. So this BH4 negative would not release H minus as an ion. It would be more covalent in nature. So that's why this NaBH4 can act as nucleophile. But sometimes what the students make mistake is that, let's suppose we have BH4 negative and we have a negative charge here. So let's suppose we have an electrophile, and this sometimes students do this negative charge, they attach this negative charge to this electrophile and make a bond. Actually this is not possible, because here you can see this boron have 10 electrons. This cannot be possible, right? Boron cannot make 5 bonds. Boron cannot make 5 bonds. This cannot be possible. So what actually happen, if we have electrophile, this borohydride basically releases H minus, basically not like H minus, but it actually donates boron hydrogen sigma electrons to this electrophile, and we have EH bond formation and BS3. So here basically boron hydrogen sigma electron transfer take place, and hence like NaBH4 act as a good reagent for reducing aldehyde and ketones to alcohols, because here it basically donates boron hydrogen sigma bond but not directly H minus or hydride ion. So how it works, let's suppose uh, we have a alcohol aldehyde, like in NaBH4 BH4 negative, what it will do, it will basically uh, transfer the boron hydrogen sigma bond like this. Let's suppose we have hydrogen boron and rest of the hydrogen is here. It actually transfer this sigma bond to this carbon group, and the pi bond breaks, leads to alkoxide formation. It will give BS3, but BS3 is also again a good electrophile, but it can be stabilized by this alkoxide. This oxygen negative charge donates its electron to BS3, and you will see again oxygen forming BS3. Again boron have negative charge. So again this boron negative charge can donate the boron hydrogen sigma bond to another molecule of aldehyde or ketone, and so on the reaction will go forward. But the main thing which we have to understand is that if we have this aldehyde, or you can take ketone also, and on adding NaBH4, first thing we have formation of alkoxide ion. Alkoxide ion. Now as NaBH4 is soluble in water and ethanol, it can take this oxygen negative can take hydrogen from water and get protonated, which leads to formation of alcohol. So some of the example which we can use are like, let's suppose we have this compound, on adding NaBH4 in water. It will give us this compound. Or we can just use methanol as a solvent. The methanol will again just protonate the alkoxide so formed and lead to formation of this alcohol. But this NaBH4 is relatively less reactive. It only reacts with aldehydes and ketone. So NaBH4 only reacts with aldehyde and ketones. But not with esters or amide. It literally do not give any reaction. For example, if we have this compound, okay, I should change the color. Okay, let's suppose if we have this compound, you can see this is a ester group and this is just a ketone. On adding NaBH4, let's suppose we take ethanol this in this case. This NaBH4 do not reduce the ester group. It will remain inactive or remain like this only, but it will reduce the ketone to give this secondary alcohol. But if we just wanted to reduce this ester or amide group, so we need to increase the reactivity of this reducing agent. So here we have another reducing agent, LiAlH4. It is a superb reducing agent, LiAlH4. This is lithium aluminium hydride. Being more reactive as compared to NaBH4, we cannot use it in water. As with water, it basically reacts very fast. So why it is reacting more fast? Why it is more reactive as compared to NaBH4? This is because if we just compare NaBH4 boron hydrogen bond with aluminium hydrogen bond of LiLH4, so this aluminium hydrogen bond is relatively more ionic, relatively more ionic. So it will basically releases, or it is easy to break this bond, and hence this LiLH4 is more reactive, easy to break bond. And hence this LiLH4 we cannot use with the water, because in LiLH4 the aluminium hydride reacts with water and produces hydrogen gas, and sometimes this reaction get explosive also. So we generally use it with alcohols, but this LaLH4 reacts with esters, aldehyde, ketones, amide, etc. Being more reactive, lithium aluminum hydride react with aldehydes, ketones, esters, amide, carboxylic acid, etc. But for this video, we just talk about the aldehydes and ketones, because the purpose of this video is just the reactions of aldehyde and ketones, the hydride attack on aldehyde and ketones. So thank you for watching the video.